Alright, we want to show that this function is not differentiable at the origin, and maybe you could apply one of the previous problems. I think it was 2-4. You might be able to, you might not. I'm not 100% sure. And here's something that I know for sure you can do. So we're going to assume for contradiction that f is differentiable at 0, 0. So if it's differentiable, then it has a derivative. So with we haven't really been referring to this as the derivative. So let's just say that there exists a lambda h, some linear function lambda from R2 to R, because f is from R2 to R. So lambda is, for lambda to be linear from R2 to R, that means we can write it as a form, say lambda of h comma k is equal to, well, actually, when we're defining it, let's say lambda of x comma y is ax plus by. Where a and b are some real numbers. And we also know that the limit as h comma k goes to the origin 0, 0 of, let's see here, so on top we've got f of hk minus f of 0, 0 minus lambda hk, all divided by the norm of hk. So this limit has to be equal to 0. But let's take another step and actually write out what this is. So this is the same as the limit as hk goes to the origin of, now on the bottom you've got the norm of h comma k, so I'll just bring that out front and write it as 1 over the square root of h squared plus k squared. And then on top, we'll just multiply this by norm of, now f of h comma k is just the square root of the absolute value of h times k. And see here, we subtract f of 0, 0 is just the square root of 0, which is 0, so that drops out. Then we also subtract lambda of hk, so this is minus ah minus bk, and again this is equal to 0. Fix some number m greater than 0, and let gamma be the curve of points given by h comma k, where k equals m times h. So what we're doing here is we're taking some m greater than 0, and that's going to be the slope of this line. So y equals mx. And so this is the x-axis, this is the y-axis, and we're going to take the limit as h comma k approaches the origin along this particular line. So what we're going to do is we're going to obtain a contradiction by proving that this limit as h comma k, the limit of the previous thing that needs to be 0, this limit needs to be 0 as h comma k approaches the origin. And in particular, it needs to be 0 for every possible path you could take to the origin. And so in particular, it needs to hold for every path of this form, where you just take a line of some given slope. This is a kind of technique that I remember providing a lot of examples in this when I was TAing for Calc 2. So this is a really, or it might be more Calc 3-ish. It's more like if you're taking limits of with respect to two separate variables. This is something that's likely to come up. Like if you want to take the limit to a point in R2, then every single path needs to be the same. So in particular, you want to look at lines. Looking at lines is typically the easiest way to find contradictions to limits existing. So anyways, let gamma be this curve. Then 0 has to equal the limit as h comma k approaches 0, 0 along gamma of this thing. Guess I should make that a little smaller because it's part of the subscript. So along gamma of this whole thing. But now we can actually start to replace some things because this is equal to the limit. Well, if h comma k is approaching 0, 0, then all we need to do is take h to 0, and since k is equal to m times h, then as h approaches 0, k also approaches 0. So all we need to do is take k to 0, and then we replace all instances of k with m times h, because that's what it means to be in this on this curve gamma. So anyways, we take h squared plus, and now we'll have m squared h squared, because k equals mh and we're squaring it. Then we multiply by the square root of h times, well, in absolute value, h times mh minus ah minus bmh. No, bmh. There we go. Alright, so now this is the limit as h goes to 0 of, let's see here, we can factor out an h squared in the denominator here underneath the square root, and then when we bring the h squared outside the square root, it becomes just an h. So we get h times the square root of, and after we've factored out the h's, we just have 1 plus m squared. This is all on the bottom here. Then on the inside, we've got the square root of, well, we've got h times h, and we can bring that out of the square root and get just h, and we multiply by the square root of m. M is positive, so we don't worry about the absolute value. And minus ah minus bmh. And of course, h is, oh no, we do need the absolute values here because h could be negative. And so we'll put the h here as well, or put the absolute values there as well. But here it doesn't matter because this entire term is in absolute value, or this entire thing here is in absolute value. So the absolute value on this particular h on the inside won't really matter once we factor out the h. So here I'll write out another step. So we got h on the bottom in absolute value. We've got a 1 plus m squared, being square rooted. Now we factor out that h, and we'll get m minus a minus b times the norm of h. And then we can cancel this with this. And so this is going to be, and once we've done this, we've gotten rid of all the h's, and so there's no limits anymore. And so we can just take the absolute value of square root of m minus a minus b over square root of 1 plus m squared. So what does this mean? So if 0 equals this thing, and this thing in the denominator is going to be positive, because m is positive, so 1 plus m squared is positive, so the square root of that is positive. And so for this thing to be 0, the numerator needs to be 0. So 0 equals the absolute value of m minus a minus b. Let's see here. So I actually, when I was writing this out, I sort of was stupid and didn't include the absolute values. And so it's like, it's, so it's, so the proof that I have written down doesn't work, but you can sort of wing it, because once you see this, 0 needs to equal. So we know that A and B need to be chosen in such a way that this equation holds for every single choice of m greater than 0. And intuitively, you can just sort of think like there's no way that this equality could possibly hold for every single m. And so we're basically done at this point. However, just for the sake of being a little bit more detailed, I'll actually go through and prove that A equals, or get an actual contradiction here. So, let's see here. So let's say, let's see here. Is there any reason we chose m greater than 0 instead of m greater than or equal to 0? No, there's not, because we still can divide. We still have a 1 plus m squared there in the denominator here. We won't be dividing by 0 if we use m equals 0. So if m equals 0, this becomes 0 is equal to norm of a minus b. Okay. So if you factor out a -1, you get a plus b equals 0. We just factored out a -1. So the absolute value of a plus b equals 0. And if the a and b are real numbers, so if the absolute value of if a plus b in absolute value is 0, then it needs to be the case that a plus b equals 0. So a equals minus b. Okay? So then 0 equals, we have square root of m minus a minus, and then b we can replace with a negative a. So this is equal to square root of m. And then we have minus a, and we subtract negative a, we get minus a plus a, which is 0. So we just have square root of m. Okay. And this cannot hold for every single m greater than or equal to 0. Okay, so we have arrived at a contradiction. And hence, f is not differentiable at 0, 0, which is what we had assumed way at the very beginning of this problem. We assumed for contradiction that f is differentiable at 0, 0. We did a bunch of work, and we got a contradiction. Therefore, it cannot be the case that f is differentiable at 0, 0. And that's what we wanted to prove, and so we are done.